Hello everyone. So, for today's video, we're going to go ahead and talk about solving exponential equations and solving logarithmic equations, right? So the past 3 lecture videos now, we've gone and established this idea of exponentials and logarithms and some properties behind them. So now we're finally going to bring that all together and solve equations that involve these things. In order to do that, we're going to introduce 2 things I like to call our mantra 1 and mantra 2 for today's videos. These will essentially be the techniques that you always use when trying to solve an exponential equation or a logarithmic equation. So, why don't we go ahead and just get right into that now. Okay, so before we get into the new material for today, I want to go ahead and go back and just kind of recall everything we know up until now. And what I mean by that exactly is I want to go and consider these 2 following examples. And how would we solve them with the tools we have as of right now. So for the first one, 2 to the x equals 32. That's a pretty straightforward exponential equation. And for us, right now, there isn't much we can do in order to solve this. The only real technique we have to solve this right now is just to understand the powers of 2. And understand that 32 is indeed a power of 2. It's when x equals 5. It is the 5th power of 2. That's pretty much all we have right now. It's just our understanding of exponents and how they relate to certain numbers. So 2 squared is 4, 2 cubed is 8, so on and so forth. Okay? And then also for this logarithmic problem, right, we have our game we used to play. And that was just taking the logarithm, converting it to an exponential, right? So taking the base, which is base 10, raising it to the power of the value you want to equal, so -1, and setting this equal to the value inside the logarithm, x. So in other words, x equals 1 over 10. That's how we solve logarithms pretty much at this point, is converting to an exponential, and then again, just going back to what we did up here, and using our understanding of exponents for certain nice numbers, like 2, 10, so on and so forth. Now, that's all nice and all, but these 2 techniques, if you want to even call them that we've just employed to solve these 2 examples, only really work for very simple exponentials and logarithmic equations, right? Things that have nice answers, 5, 1 over 10, very nice answers. But most of the equations we're going to work with aren't going to be simple, aren't going to have nice answers. So that's why we're going to spend today's video talking more about how to develop techniques that solve these more complicated or more robust exponential and logarithmic expressions. Alright, so let's go ahead and discuss more about that. Okay, so here's going to be that first mantra of the day I've already briefly mentioned. This will be our mantra or technique for solving exponentials, okay? It goes like this. To get rid of an exponential with base a, take log base a of both sides. Alright, so just to review the notation that's being used here. Base a, what is base a referring to? Well, in an exponential, like a to the power of x, and so a number to a variable power, that number, the base, that is our base a. Okay? So, that is the technique. Very straightforward, not much going on here. It's just take a logarithm both sides. Why do we want to take the logarithm both sides? Well, again, always remember, so this comes from inverse property. Right. So yeah, why in an exponential do we take log on both sides? Again, that idea of inverses. If you apply the proper logarithm, you are applying the inverse. Inverses cancel each other out. So we're going to be canceling out the exponential with the logarithm. That's the core idea of this technique. So just to write it in a bit more general and how formulaically, right? If I had the exponential equation, a to the power of x equals y, and I want to solve for x, let's say, so I want to remove the exponential. That's the biggest obstacle in my way, is the exponential. So in order to remove that, we apply this mantra 1 technique. We take log base a of both sides, and I'm going to go ahead and erase this quick notes. Take a note of this, right? It is important to realize that this whole technique is coming from the inverse property. So, quick second to pause the video to get that copied. Okay, so, alright, so here's the general application of the mantra 1. Have our exponential. Take log base a of both sides. important to note is that this is base a, right? Because our exponential has base a, so just make sure you match the bases. So we have these two. Now right here in our next step, right here is where we're going to apply the inverse property. So inverse property tells us that since, well actually we can go back and let's recall it, just say it out loud to ourselves. What was the inverse property we said before? We said that inverse property was log base a of a equals 1, right? Log base a of a equals 1. So over here we can apply our power property of logarithms, what we talked about last lecture video, and that we can take this power, we can bring it out to the front. So I'm going to have x times log base a of a equals log base a of y, right? And as we just mentioned, inverse property log base a of a, that is going to be 1. So we have that x equals log base a of y. And there you go. That is the application of this mantra 1. This is how you solve exponential equations. If you have a variable and a power, you want to solve for that variable, you're going to need to take a logarithm on both sides of your equation at some point. And that's the general way of solving it. Oh, I guess I should say power property. And then right here, between these two steps, was inverse property. So this technique is essentially using two properties that we've talked about in this class up until now. So there's the general example. Definitely pause and get this written down. I think I realize now I should have written this in a different color. Oh well. But go and pause and get this written down. And then we'll do a very quick example before we move on to the second technique. So pause. Okay, so I'm going to erase this general part. Okay, so a quick example. Let's just go back and let's look at that original exponential equation we considered. 2 to the x equals 32, right? So we understand the answer is 5 because we can see that without much difficulty with our understanding of exponents. But just to apply this mantra so we can see what actually is happening, here, if I wanted to solve this, I would take a log base 2 of both sides. I would take a log base 2 of both sides. Then again, apply power property. We get x log base 2 of 2 equals log base 2 32. Alright, that log base 2, that is a 1. So I now have x equals log base 2 of 32. We need to solve this number. Right, but we can't do log base 2s in our calculator. So how would I solve that? Well, we talked about this in last lecture video. If I have a base logarithm that's not 10 or e, simply use our change of base formula and then solve that in our calculator. So we're going to get x equals ln of 32 divided by ln of 2. And we plug that into our calculator. ln 32 divided by ln 2 is indeed 5. Still get the same results. So, yeah, so when we actually solve this exponential, more formally, this is what's actually happening. But for us, for a simple problem like this, we can just simply do it in our head. As we're going to see though, with some future examples, not going to be so simple, need to go through the process of applying this mantra or this technique. Alright, so that's the first one. Let's go ahead and talk now about how we're going to solve logarithmic equations. Okay, so our second mantra, or our second technique for today, will be in regards to solving logarithms, or equations with logarithms. And it goes like this. To get rid of a log base a, make both sides of the equation powers of exponentials with a base a. Okay? So, again, just recalling what it means to be base a of an exponential and a logarithm. Now, getting into the general or more formulaic way of writing this, if we have a logarithmic equation, so a standard one like log base a of x equals y, in order to solve this logarithmic equation for x, we would apply this technique, and this technique says take both sides of your equation, so log base a of x and y, and make both sides powers of exponentials with base a. And that's exactly what we've done in this step right here. So we have two exponentials with base a, and each power on these exponentials are both sides of that original equation. So one power is log base a, the other power is y, okay? So right here, this is us setting original equation to be powers of exponentials. I forgot how to spell exponentials. There we go. So there it is. That's us setting both sides of our original equation to become powers of exponentials, both with base a. And then again, right here, right, we've talked about this before, we have an exponential with base a to take into the power, or with the power of log base a. There again is the application of inverse property. Inverse property tells us the exponential and the logarithm cancel, and what we're left with is x, okay? So again, right here to here, that is inverse property. And so we are left with that x has to equal a to the power of y, all right? So here it is. This is how we're going to solve logarithms from now on, moving forward in this class, is we apply this technique. Again, we take the inverse on both sides of the equation, so the inverse of the logarithm is just that exponential. All right, so again, oh, excuse me, I have to let out the cat. Okay, so again, let's move back now. Go ahead, take a moment, pause the video, get this part written down. I'm going to do a very quick example afterwards, so go ahead and pause now. Okay, so just do a very quick example. Again, referring back to that one we started today's lecture video with, if I have log of x equals -1, let's go ahead and apply this mantra 2 technique. So we're going to have 10 to the log of x equals 10 to the -1. Again, log with no base is base 10. So I want to take both sides of my equation and make them powers of exponentials with base 10. This is us applying that technique. Inverse property kicks in. I'm left with x equals 10 to the -1, which is the same as 1 over 10. And there you go. You solve the technique. So, that's it. These are the two techniques. Very simple techniques. They're not complicated, very straightforward, but very powerful. Use them all the time whenever you do any equation that involves logarithms, exponentials, and you've got to solve for a variable. You're going to use them. They just become second nature. Okay? So, let's go ahead now and move into more complicated examples. Okay, so for the rest of this lecture video, we're just going to be doing some examples from now on. We're going to go ahead and walk through first some exponential examples, then we'll do some logarithmic examples. So to start, let's consider the following exponential equation. 62 minus 10 to the power of x equals 24, and we want to solve this. Alright, so this will be us getting used to using those two techniques we've introduced. Now, just like any other time we're trying to solve a variable, or trying to solve for a variable, we want to isolate that variable. So we're going to want to isolate the exponential term. So still just want to isolate variable. So in that regards, we'll subtract 62 to both sides, and we'll get minus 10 to the x equals minus 38. Okay? Dividing by the negatives, we can make both those positives, and here we use that first technique. Use that mantra 1. We're going to have log of 10 to the x equals log of 38. So x equals 38. Alright, not that complicated. Main purpose behind this example was just to, again, iterate. When we're using these techniques, before we get to use the technique, we have to isolate, alright? So, before you use the techniques, or the mantras, I guess, make sure to isolate the variables. Oh, to isolate the exponential. The variable. I'll say exponential. Okay. So yeah, that's pretty much the main purpose of this example, was just to show that before we use these techniques, we got to make sure we isolate, and then we can use them. All right. But besides that, a very straightforward example. So now let's go ahead and have you guys try doing one. Gonna go ahead and erase the board now. So if you haven't done so already, pause. Make sure you get all this work written down. Okay, so let's go ahead and do another very quick example. Have you guys do it. Going to go ahead and erase. Alright, so go ahead and do solve the following equation. 2 to the e to the x minus 7 equals 23. So 2 times e to the power x minus 7 equals 23. Go ahead and take a couple minutes now to solve this equation. And after you solve for it, I'll go ahead and write my answer on the board, and we'll see if our answers match up. So go ahead and solve now. Okay, so hopefully you gave the problem a shot. I'll go ahead and write my answer up on the board now. What I got was that x must equal ln of 15. Alright? So, hopefully we got the same answer. If not, double check your work. If you still feel confident that you're right, that's good. Send me an email, we can discuss, because who knows, maybe I made a mistake. Besides that, that's it for this example. Let's go ahead and move on into our next example. Okay, so let's just go ahead and ramp up the difficulty a little bit and consider the following equation. 4 times 4 to the power of 2t minus 7 plus 14 equals 10. Let's go ahead and solve this. Great first step, subtract 14 to both sides. So we're going to get 4 times 4 to the 2t minus 7 equals 96. Alright? Now here is where we're going to have several options. Again, like trying to enforce that idea, I mentioned it, I think it was last lecture video. Solving a problem, not necessarily linear. The way I do it doesn't necessarily have to be the way you do it, as long as we're using proper techniques, using concepts and ideas appropriately. There are many paths with which we can solve a problem. Here's another example of that. I can have 2 different ways to do it at this point. I could divide by 4 to both sides and isolate that exponential. Or what I can see is I can recognize that this is I have 2 4's here. I can multiply this 4 in, and I can apply the property of exponents in that this is a 4 to the power of 1. So I have 2 exponentials of the same base, 4 and 4, and I'm multiplying together. So properties of exponents tell me to add the exponents. And this will become 4 to the 2t minus 6 equals 96. Alright, and then from here, I now have that standard exponential equation I was looking for. I can start using those techniques we've introduced. I can take a log base 4 on both sides. I can take a log base 4 on both sides. The log and the exponential cancel, so I'll have 2t minus 6 equals log base 4 of 96. Okay? So now we're going to go ahead and continue, but I'm going to need some more board space, so if you haven't done so already, pause the video to get this work copy down, and we're going to erase and start at the top of the board. So go and pause now. Okay, so alright, so, oh, my bad. Log base 4, 96. Now, at this point, okay, so actually, let's continue, let's solve for t, and I'll get to that point I want to make later. Okay, so we'll just continue solving for t, so we're going to add 6 to both sides. Alright, and then t, divide by 2 to both sides. So we get that, alright? And this would be our final answer. So this would be our final answer in exact form. Right? This is our final answer in exact form. However, we should get some practice in with giving the decimal form of the answer as well, right? Because if I ask you to give a decimal answer, then we're going to need to know how to calculate this. So again, the issue of I have a log base 4, our scientific calculators can't do base 4, have to again use that change of base formula. So just to make sure we get practice with that, why don't we go ahead and do that now. So go and pause the video, use your calculator, get the decimal answer of this is, you're going to need to use change of base on this base 4 logarithm, and after you unpause, I'll go ahead and write down the decimal answer I got as well. Okay, so go ahead and give that a shot now. Okay, so hopefully you gave it a shot, and the answer that I got was approximately 4.64624. Let's round it up to there, up to 5 decimal places. Okay, so this is the decimal approximation I got. Make sure that you got the same thing. If not, double check your inputs. And if you still feel you're right, don't automatically assume that you're wrong. I could have easily just tongue tied. I could have easily just plugged in my values wrong to the calculator. It can be a bit tricky when trying to plug in these types of values in calculators because you got to be careful with all your parentheses and stuff like that. But that's what I got. I'm fairly certain that's correct. Regardless, so I guess I should note, this was the final answer in decimal form. And again, to jump between these two forms, we had to use change of base. Okay, so yep. Again here, something I guess I should point out about this example is I kind of erased it at this point, but we should note that at the start, our power was actually a whole another equation. It was a linear equation, right? So your exponent in the exponential doesn't necessarily have to be just the variable. It could be a whole nother equation, sorry. For us, the power of the exponential was a linear equation. Alright, so the power of our exponential in this example was a linear equation. That's okay. Just means that after we apply that mantra technique, there's going to be a couple more steps we have to do in which we solve for that linear equation power. That's not a big deal. Just wanted to point that out so you guys don't get freaked out or anything if you see something like that and think like there's more complicated steps you have to do. Nope, not the case. Just go ahead, apply that technique. It'll still bring that power down by the power property, and that log and exponential will still cancel each other out, and you'll just be left with whatever secondary equation you need to solve. Okay, so that's that example. Let's actually get into, I think it's going to be our last exponential example, and it's a much more interesting type of problem, at least in my opinion it is. So let's go ahead and give that a shot. Okay, so for our next example, let's consider the following equation. E to the power 2 times x minus 7 times e to the power x plus 12 equals 0. We want to solve this now. So, in these past examples we've done, we went through the process of isolating that exponential, right? And then using that mantra technique. Now, for this one, we can already see that it's going to be a bit of a challenge to just try to brute force isolate that exponential. And why is that? Because we have 2 exponentials here, and the important note is that they have 2 different powers. So I can't easily combine these exponentials, and I can't, in a more straightforward manner, isolate it. So we're going to have to dig deeper here. We're going to have to take a harder look at this problem. And hopefully you'll be able to see it, kind of what I'm alluding to. And if not, the title of the problem kind of gives it away, right? So I call this a quadratic-like equation. So what we can notice is that I can make a very slight alteration to how I write this, and that I can write this exponential, or this exponential equation as e to the x. Oh, let me give myself a bit more room. I can rewrite this into e to the x squared minus 7 times e to the x plus 12 equals 0, right? Again, properties of exponents, I have a power taken to another power, so it tells us to multiply. Exactly what we have right there. So I can rewrite it like this. And hopefully once we write it like this, it starts becoming a bit more clear, right? Imagine if I wrote u instead of e to the x, right? So I have u squared minus 7u plus 12 equals 0. And lo and behold, that looks exactly like a quadratic equation. We know how to solve these, okay? And hopefully everything I've done right here seems a bit similar because we've done this before in our class. Going back, man, like, I think even before the shelter in place took place, we've talked about a technique like this. This is that u substitution technique we used before. Here's our u sub technique, right? This is us letting u equal e to the x. If we let u equal e to the x, this exponential can be rewritten into this nice quadratic equation. So, again, this is a great example that drives home that point. The things we learned in this class are not isolated, right? We're using all these techniques together. We're building on top of everything we've learned, mingling ideas, mingling techniques, and bringing them all together in problems like this in which we use multiple techniques to solve a single equation. So here we have just applied our u sub technique. We have rewritten this exponential into a nice quadratic. And why do we want to do that? Because we know how to solve quadratics. We know how to isolate the variable here. So for us, we now have u squared minus 7u plus 12. We can go through several techniques at this point. We could factor, we could use quadratic formula, we can complete the square. Have several things to do. For me, this one I can easily factor in my head, so I'm going to do just that. This can be factored into u minus 4 times u minus 3 equals 0. So that is the quadratic factored. Alright, so now I need to solve, continue solving from here. As you can see though, ran out of board space, so go ahead and take a moment to pause the video and get all this copied down. Keynote right here is that we have used the u sub technique. Alright, we notice this is a quadratic-like equation, so we use that u sub technique. Okay, so go and take a moment to pause the video now. Okay, so then, starting from the top, we have u minus 4 times u minus 3. So we have two unknowns being multiplied together equals 0. Again, that tells us, going all the way back, that zero product property, I believe that's what it was called, that tells us u minus 4 has to equal 0, or u minus 3 has to equal 0, so we have to let them both equal 0. Solving that, we get u equals 4 and u equals 3. Good job, us. Solve the problem. We are done, right? No, of course not. We've talked about this all the time before. When using u sub technique, we have to always remember we are not solving for the variable u. That was not the variable we started with. We are trying to solve for the variable x, alright? So we have to undo the u sub. Have to undo it, alright? So in that regards, we recall we let u equal e to the power x, so I now have two equations. I have e to the power x equals 4, and I have e to the power x equals 3. Alright. Solving this, I need to take an ln on both sides. ln. ln. Oh. ln. And ln. Beautiful. Inverse property applies. Power property applies. We bring that variable to the front. So I get x equals ln 4 and ln 3. There you go. Okay? And that's how you do a problem like this. Like I said, I like this problem. It uses that quadratic. It uses that u sub. It uses so many cool techniques we've talked about in this class that just so cool. Alright then. But with that out of the way, let's go and have you guys try doing a very similar example now. But before that, go ahead and pause the video now, get all this work copied down, and we can have you guys try doing one yourselves. So go ahead and pause now. Okay, so let's have you guys give it a shot. And go ahead and try solving for yourselves this following equation. 10 to the 2x minus 8 times 10 to the x plus 12 equals 0. Alright? So go and take a moment, try this problem on your own. After you unpause the video, I'll go ahead and write my answer on the board and we'll compare. So go and pause the video now. Okay, so hopefully you gave the problem a shot and you got a final answer. So the answer that I got was x equals log of 6 and log 2, right? This is a quadratic-like problem. Not too surprising for us that we get two answers, right? Quadratics at most can have two answers. So there you go. Here's what I got. Log base 6 and log base 2. So hopefully you got the same. If not, double check your work. If you still feel confident, shoot me an email. We can discuss the problem. But I'm fairly certain those answers are correct. But besides that, that's it for the exponential type problems. All right, we've gotten some experience now applying that mantra technique, understanding how sometimes we need to fall back to our previous techniques, U sub, things like that. So with that out of the way, let's go ahead and move on now into some examples involving logarithmic equations. Okay, so let's go ahead and try doing now some logarithmic examples. On the start, we'll consider this following example. 4 plus 3 times ln of x equals 16. Let's go ahead and solve this equation, all right? So just like with the exponentials, just like with any equation we're trying to solve for a variable, isolate that variable. So to start, we'll subtract by 4. Ooh, bless me. So we get 3 ln of x equals 12. All right, divide by 3. ln of x equals 4. Okay? So here we've successfully isolated the logarithmic expression. Now we can apply that mantra to that second technique we introduced today and how to solve logarithmic equations. Might as well give some more board space to it, so go ahead and pause the video, get all these basic operation steps written down, and we'll start from the top. Okay. So, we now have that ln x equals 4, right? So, how do we solve this? Well, we apply that technique. That technique says, take both sides of your equation, make them powers with the base a of the base of your logarithm, all right? So we have ln is log base e. So I want to take both sides of these equation, I want to make them powers of e. So in other words, e to the ln of x equals e to the 4. Again, we get to apply that inverse property. These cancel out, so we're left with x equals e to the 4. And there you go. We've solved the equation with the logarithmic portion to it. I don't know where I was going there. But regardless, that's it for this equation or example. Not very complicated. Again, just walking through the process like we would do for any equation which we're solving for a variable. But towards the end, we get to apply this new technique we've introduced. So now, let's go ahead and have you guys do a similar type problem, and we can go ahead and compare answers, the whole shebang. So, let's go ahead and do that now. But before that, go ahead and pause the video, get these last couple steps written down. Alright, so now for you guys to try, go ahead and try solving this following logarithmic equation. Log base 3 of 2x plus 1 equals 2. Alright, so go and take a couple moments now, pause the video, try solving this try solving this equation, alright? Using that new technique we've talked about, just walk through the steps. So go and pause the video now. Okay, so hopefully you gave the problem a shot, and if you did, let's now compare answers. The answer that I got was x equals 4. X equals 4 was what I managed to get for that value. So, hopefully we got the same answer. If not, double check your work. I'm 100% certain that this is actually correct, so if you didn't get 4, go ahead and work through your problem one more time, try to see if you can find the mistake. But besides that, let's go ahead and try moving into a more complicated logarithmic problem now. Okay, so let's go ahead and try another logarithm example. Let's consider this following equation. Log base 6 of x plus log base 6 of x plus 5 equals 2. And we want to solve this, alright? So again, just like with that quadratic exponential problem, right? We can't just right off the bat try to push forward towards isolating that logarithm, because we have two different logs with two different values inside. So we can't just kind of brute force it. We're going to need to take a deeper look, got to step back and think to ourselves, before I start trying to isolate this logarithm, what else can I do? Alright, so we take a moment and we think, and hopefully we just start thinking all along the lines where we're thinking of, well, what's the core idea of this problem? The core idea is that those log values, right? That's where the biggest obstacles in our way right now. So we start thinking about logs. What about logs could I use? What techniques, ideas, properties could I apply here that can make my life easier? And once we're thinking along those lines, hopefully it doesn't take us too long to realize and recall, oh, would you look at that? What am I doing here exactly in this problem? I'm adding logarithms. Not only that, I'm adding logarithms with the same base, okay? So right there is a direct application of that product property of logarithms. Log of A times B equals log A plus log B. So right here we have our product property. And why would that be helpful for us to use? Because that product property will take these two separate logs and make it into a single log, effectively isolating that logarithm. So let's go ahead and do just that. So using product property, we end up with log base 6 of x times x plus 5 equals 2. Just like that, we've isolated the logarithm. Now we can use that mantra 2 technique we talked about. Alright, in order to do that, we take both sides of our equation, we make them powers of exponentials with the base of the log, that being 6. So we make these both powers of 6. So we get 6 to the power of log base 6, and that looks like a u, log base 6 of x times x plus 5 equals 6 squared. Alright? Applying that inverse property, the log and the exponential cancels. We're left with x times x plus 5 equals 36. And from here, we have removed all those nasty things that make the problem seem complicated, and we reverted this back to a pretty straightforward and standard quadratic equation. Now we can go ahead and solve that. So, in order to solve this though, I'm going to need the board space. So go and pause the video now, get all this work copied down, then we'll go ahead and tackle the remainder of the problem. Guess I should point it out now, there is going to be a very important note at the end of this problem. So don't feel like you can solve it just yet, because there is something we need to take very special note of. So let's go ahead and talk about that now actually. So, starting from the top, we have x times x plus 5 equals 36. So distributing that out and moving that negative 36 over, moving that 36 over, we're going to get x squared plus 5x minus 36 equals 0. So, just your standard everyday quadratic equation. This we can solve pretty much with our eyes closed at this point. So, this one can be factored. It can be factored into x plus 9 times x minus 4. Alright, so that's going to lead us to x equals minus 9 and x equals 4. And as I mentioned right there, we would normally say, great, I've solved for my x variable, those are my solutions. Now this is where we got to say, okay, wait a minute, let's take a step back, because there's something important going on here. And this is going to be the most important example for today because of this, what we're about to talk about right now. Now, as always, whenever we do math, there's the single most important step that is universal throughout every single technique, property, whatever. Like every single way you can solve a problem always ends with this. And of course, it's a step that no one ever does. We always skip it. Even I'm skipping, even though I keep on telling you guys to do it. And of course, what is that? That is always to check your answer. Check that your solution is correct. Plug it back in, okay? So let's do exactly that. Let's plug back in that x equals negative 9. Let's see what happens. So, in order to do that, you're going to need to erase the board. So if you haven't done so already, go and pause the video and get this copied down. Alright, so let's go and plug in that negative 9. So if we have x equals -9 and I plug that in, what I have then is log base 6 of -9 plus log base 6 of -9 plus 5 equals 2. Alright. And right here, after we plug that in, this is where our kind of alarm bell should be going off in our head. And why is that? Because right here, I have log of a negative number. However, if you recall when we first introduced logarithms, if I had a log, we said that for log base a, where a is any base, we said that the domain of this function was 0 to infinity. Oh, actually, you know what? Does that include 0? Log of 0? No, doesn't actually include 0. We said the domain was 0 to infinity excluding 0. In other words, the domain of any logarithm is only positive numbers. You cannot plug a negative number into a logarithm like this, okay? Same here. Simplifying that down, that's log of -4, still doesn't work, alright? So, this is a value that lies outside the domain of the log function, so therefore it cannot be a solution. Because remember, domain is the collection of all x values that produce valid outputs. So this does not produce a valid output. It does not lie within our domain. It is not a solution. So -9 lies outside the domain of log base 6 of x. That is the very important notes we need to be aware of for this problem. And it's something you need to be aware of whenever you're solving logarithms, is that they have a very specific domain. So make sure you're aware of what their domain is. And when you're looking at the solutions, make sure you're aware that sometimes, and quite often, they can produce extraneous solutions. They can produce those false solutions. Alright? So just to kind of write that all on the board, what I just said, going to need to erase. So go to this point, go and pause the video. Get all this copied down. These are some important notes, so make sure you get them copied down. So go and do that now. Okay, so just to write on the board what I just said. Make sure to check for extraneous solutions when solving logs. Okay, so for us, x equals 4 is the answer, or is the solution, and x equals -9 was a false solution. False. Alright. There it is. Okay? So, with that out of the way, that was a pretty important example, so let's actually have you guys do a very similar example, alright? Have you guys take a crack at it. So, go and take a moment now to pause the video and get this all copied down, then we'll go ahead and have you guys give it a shot. So pause now. Alright, so for you guys, go ahead and consider the following equation. Log base 2 of x plus log base 2 of x plus 6 plus 3 equals 7. Alright, here's your equation. Go ahead and try solving it now. After you pause the video and solve it now. After you unpause, I'll go ahead and write my answer and we'll see if we match up. So go ahead, pause now. Okay, so hopefully you gave the problem a shot. And if you did, let's compare answers. Here is the answer I got. X equals 2 is the solution. And x equals -8 was a false solution. So go and take a moment, compare answers. Hopefully got the same. If not, double check your work. Again, I am actually very confident that this is the correct answer. So if you did not match up with me, definitely double check your work. If you can't find your error, just email me, send me your work, and we can go and discuss that. But besides that, that's it for today's lecture video. Hope everyone continues to stay safe, stay healthy, have a nice rest of your day whenever you happen to watch this video, and I'll see you guys in the next one. See you later.